And the other way that you can get your shunt is to estimate it. This is assuming that you have a P little a O2 greater than 100 and your CAV O2 is 5, which is about normal. And so the rule of thumb, if you're on 100%, every 100 torr of difference equals about 5% shunt. Now, there's another way also that you can estimate shunt, and that is by AADO2s of 50. If your AADO2, instead of being 100, like in this example, when breathing, if every 100 of torr, AA difference is 5%, every 50 they estimate to be 2%. So every 50 is 2%, and you can put 50 in here, and remember that you're going to multiply here by 2. So this would be one way that you could figure it out. Take the AA gradient divided by 100 if you want to use the 5, or 50 if you want to use the 2, and that equals 3, and then 3 times 5 is 15. So that's an easy way to kind of estimate your shunt. And again, this could easily just be 300 divided by 50, which would be 6, and then it would be 6 times 2, which would be 12. So you see, 12, 15, they're going to be different, and these are an estimate. So you have to keep that in mind, that there are 2 different ways to estimate it, and it is an estimate. So it's not going to be as precise as the way that we just went over, but it's easier to do. The other thing you want to keep in mind is that when you calculated the shunt, you needed that venous blood sample. So you want to keep in mind that that mixed venous, the venous sample, had to be gotten from a pulmonary artery catheter or Swan-Ganz catheter. So it's in the pulmonary artery, so that would be venous blood before it goes to the lungs. And you have to pull it very slowly because you don't want to pull the blood coming from the capillary that already got in contact with the alveoli. So you have to pull very slowly to draw the sample from that line. So you're going to pull venous blood that's coming from the right ventricle into the pulmonary artery. And so there are methods to estimate that calculation, and they are based on the AA gradients. This is just some normal parameters that I put in here for you to refresh your memory about what a normal SAT would look like from a venous sample, and what a normal SAT would, PO2 from a venous sample, 38 to 42, the saturation being 68 to 77, and the content being 14 to 16. So what can cause changes in that venous content? The venous content on the venous blood gas is an important reflection of how the cardiac output is, because if you have good saturation in your arterial system, then you should be normal in your venous side too, right? Well, there are changes that can occur, like if you don't have enough hemoglobin, for instance. So you're saturated fine with what you have, and your PO2, the dissolved oxygen, is fine. But when you get to the venous side, you'll see that it's really low. And it could be because there's just not enough trucks, right? Or, of course, if your saturation and PO2 are low, your venous side is going to also be low. But here you also want to make sure that you understand that if your cardiac output is reduced, you will have a low venous SAT, because you have plenty of oxygen in your arterial side, but your heart is not pumping enough blood. And so it gets extracted. And so it leaves the venous side very low. So that's an important distinction to make. Also, you could have an increased demand for oxygen in case of fever, for instance, hyperthermia. Patients that are trauma patients or burns have a very high metabolism, and they burn up the oxygen. So their cardiac output is fine, their arterial oxygen is fine, but their venous sat is low, and it's because they're just using it up. Shivering uses it up, as well as seizures. Any hyper metabolizing state is going to use up the oxygen that's available. And then if you have an increase in your venous oxygen level, it could be because you have a high cardiac output, or because you are polycythemic or hyperoxic. So you have too much oxygen going in your artery, and the body just doesn't need that much. Now, the other things that can cause you to have a high content of venous oxygen are things like hypothermia, because you've reduced the metabolism so much that the body is not extracting the oxygen and using it. Anesthesia puts you in that same low metabolism state, so that if you have a normal cardiac output, you would see your venous saturation and content rise, because you're just not using the oxygen the way you usually do. If you are in a pharmacologic paralysis, your body, your cells are not moving. You're not moving at all. You're not needing to extract oxygen at the same rate. And so therefore your venous sat should be higher than normal. Cyanide poisoning is something that occurs, and what happens is the body is unable to take that oxygen into the cells, so it stays on the hemoglobin. So if you can't pull the oxygen off the cells, off the hemoglobin and into the cells, then it stays on the hemoglobin. And so what does that do to the venous side? It elevates it, because you got this, the same oxygen coming in from the arterial system. It doesn't unload, and it goes into the venous system. So it's elevated. And sepsis can also do that, to where people are unable to extract the oxygen needed. And I wanted to throw this in just to let you review some of this information about different cardiac types of equations that you might do. And I can put some sample problems for resistance. You may need those. So be on the lookout for utilizing these specific formulas on the next little quiz. And I'll come back to these, and we'll do a little section with these numbers too. But this shows you how to calculate stroke volume, cardiac output divided by heart rate. The stroke volume in milliliters, see, mils per minute. So you're used to seeing the cardiac output written as liters, so you want to go ahead and multiply by 1,000 and get that into milliliters. And so then you're going to divide it by the cardiac output, and in this case the heart rate was 100 per minute, and so they divided 4,000, which was our cardiac output in milliliters, divided by 100, which equals 40. And so that would be a normal stroke volume for a patient. And then it looks at cardiac index here, where you take the cardiac output divided by the body surface area. And so this gives you this is a little low, but this gives you an idea that everybody's cardiac output, what is necessary for you, is different for each person depending on their size. And so this takes into account that body surface area, compares it to the cardiac output. So if you have any questions, please feel free to ask them. I'll put up a question and answer discussion in this module. Thank you.